In this video, we solve problem 5.2.27-T. The problem statement says, based on a poll, 40% of adults believe in reincarnation. Assume that 4 adults are randomly selected and then find the indicated probability. Complete parts A through D below. Part A says, what is the probability that exactly 3 of the adults selected believe in reincarnation? And then it asks us in the fine print to round to 3 decimal places as needed. I'm going to work this out on my paper using that formula for probability for binomial distributions. Okay, so here's the probability of X successes and N trials. The way you find this is you take the probability of success and you raise it to the X power. And then you multiply by the probability of failure and you raise that to the n minus x power. And then you multiply that by the number of ways that you can choose x different positions from among n different positions. So that's the formula for a combination. So we've got n and we're choosing x of those. And we actually don't care about the order. And so we get that right there. So that's the probability of X, provided X successes and N trials. We have N trials, X successes. P is the probability of success in one trial. And Q is equal to 1 minus P. That's the probability of failure in one trial. So in order to answer this question, we just need to identify N, X, P, and Q, and then we can use this formula. I'd also like to talk about why this works. Okay, so it says, based on a poll, 40% of adults believe in reincarnation. So if we say that success is believing in reincarnation, and they ask us what is the probability that exactly 3 of the selected adults believe in reincarnation, we're saying what's the probability that X is equal to 3? Okay, well, we've selected 4 adults, so the number of trials is 4. And the probability of success in one trial, that's the probability of an adult, a randomly selected adult, believing in reincarnation, is, according to that poll, 40%. But we want that in decimal form, so you move over that decimal twice. You have 0.4 there. And if you have a 40% chance of success in one trial, you've got a 60% chance of failure in one trial. Or alternatively, you can say if you have a 40% chance of finding someone who believes in reincarnation, you have a 60% chance of finding someone who doesn't believe in reincarnation. Okay, I can find this using this formula, but I'd like to talk through why it works. Okay, so you've got n equals 4, so we'll have n factorial here, over n minus x factorial times x factorial times that probability of success raised to the x power times the probability of failure raised to the n minus x power. And n minus x is 4 minus 3, so we get a 1 there. Now if we work all of that out, this ends up being 1 factorial, which is 1, 4 factorial, you know that's 4 times 3 times 2 times 1 over 3 times 2 times 1 here. So 3 times 2 times 1 reduces and you just get 4. So we have 4 times this 0.4 cubed times 0.1 or 0.6 raised to the first. Now if you're wondering, why is it 4 times that? Well, it stems from this formula, and I'd like to talk more about where this formula comes from. So let's think about this particular example. We've got 4 adults, and we want the probability that 3 believe in reincarnation, and then there's 1 that does not believe. Well, maybe the first one does not believe. I'll use N for non-believer. And we can use B for believer. So you've got maybe a non-believer and 3 believers, or that's one way that could happen, where you have exactly 3 believers. Or you could have a believer and then a non-believer and 2 believers. Or you could have 2 believers, a non-believer and a believer. Or you could have 3 believers and a non-believer. So we actually have 4 different arrangements that feature 3 believers and 1 non-believer. Now, all of these actually have the same probability. The probability of finding a non-believer and then 3 believers is this. The probability of having a non-believer in this position is the probability of failure in one trial, or 0.6. And the probability of having a believer in the other positions is 0.4 for all of them. And if we multiply those guys together, we get 0.6 times 0.4, to the third, because we've got 3 of them. Now, if I'm looking at that second possibility where you have 3 believers and a non-believer, we have 0.6 here and 0.4 here, here, and here. So that gives me a 0.4 cubed times 0.6 again. So the probabilities are all exactly the same for each of these, but I end up having 4 of them. So the probability of having exactly 3 believers and 1 non-believer is this probability plus this probability plus this probability plus this probability But in each case, we're just multiplying, and we can multiply in any order we want. We have 0.6 times 0.4 cubed. So what we end up with is 4 times 0.6 times 0.4 cubed, which is exactly the same as what we get up here. This 4 out front is the number of ways that we can choose 3 of those positions to be believers, and then have a non-believer in that 4th position. There are 4 ways that we can do that. Another way you could think of it is this way. The number of ways that you can arrange those 3 believers in 4 positions is the same as the number of ways that you can arrange 1 non-believer in those 4 positions, with all the rest of them believers. So there's only 4 ways that you can arrange them for this to happen. And that's what this counts right here. So this over here is just the multiplication rule. That's what I use here. To get the probability that this happens, you just multiply this times this times this times this all together. Same thing here, multiply this, and this is the multiplication rule as well, and this is the multiplication rule. But if you use the multiplication rule alone, you're not going to get the right answer, because you would only be counting one of these guys. Like, let's say you said, well, what's the probability that the first person was a non-believer and the next 3 were believers? Well, you'd get this, but if you were asked for the probability that you have 3 believers and a non-believer, you'd be missing out on this probability, and this probability. And we need all 4 of them if we want the probability of selecting 3 believers, 3 people who believe in reincarnation, and then 1 that doesn't. So we can use this formula, and then let's actually work it out. When we multiply 4 times 0.6 times 0.4 to the third, which is exactly what we get here, we get 0.1536 as the probability of finding 3 people who believe in reincarnation when you randomly select 4 adults, given that the probability that a single adult believes in reincarnation is 40%. Now, we just talked about this idea. This is exactly the same thing here. Notice that this 0.4 is the probability of success in one trial. So the probability of being a believer was 0.4. And since we had 3 successes, we had 0.4 times 0.4 times 0.4. So this is p raised to the x power. That's what you see right here. And then everyone else, if they weren't a success, then they were a failure. The question is, okay, what's the probability of failure in one trial? It's q, it's that 0.6. And then you might say, how many of them do you have? Well, if you had x successes out of n trials, you have n minus x failures. So if you multiply these together, you get the probability of having the first x trials that are successful, and then the remaining n minus x trials that are failures using the multiplication rule. But that would only count one of these guys, and that's not what we want. We need to account for all of the different arrangements, all of the different ways that we could choose x of those trials out of n trials to choose from. And the number of ways that we can choose x from n is given by that formula for a combination that we studied back in chapter 4. So that's where that comes from, and that's where that comes from. It's just arrangements like this. Okay, so the answer was 0.1536. Let's go back to the homework. And the question says, round to 3 decimal places as needed. So I will round to 0.154. All right, great. Now let's answer the second question. It says, what's the probability that all of the selected adults believe in reincarnation? Well, in that one, you can use the multiplication rule. I mean, we could use the binomial formula for probability again, but we want all 4 to believe in reincarnation this time. Well, there's only actually one way for that to happen. That's if the first one believes in reincarnation, that's a 40% chance. And the next one, and the next one, and the next one. So according to the multiplication rule, we take those probabilities and we multiply them together, and we get 0.4 to the 4th, which is this. .0256. Okay, now, if you wanted to use the probability formula, you could, and I want to show you that you get exactly the same answer. So what's the probability of 4 successes and 4 trials? Well, if n equals 4, we've got 4 factorial up here. Then we've got n minus x factorial times x factorial times the probability of success in one trial raised to the number of successes times the probability of failure in one trial raised to the number of failures. Well, any number to the 0 is 1. And this 0 factorial is 1. And 4 factorial over 4 factorial is 1. And so what we end up with is 0.4 raised to the 4th, which is 0.0256. And that's the probability of getting x successes in 4 trials using that formula. But again, it's the same as what you would get using the multiplication rule, because there's only one way for all 4 of those chosen to believe in reincarnation. And if we want the probability associated with that one way, we just take the probability that the first one's a believer and multiply by the probability that the second one is a believer in reincarnation, and so on until we get that number. So let's go back to our homework. And we want to round to 1 or 3 decimal places as needed. So that's going to round to 0.026. And then the next question says, what's the probability that at least 3 of the selected adults believe in reincarnation? At least 3. Well, that's a little different, isn't it? Let's go to our paper. Oops, hi. That was the wrong thing. I was supposed to share my paper with you. Okay. Well, the probability that at least 3 adults believe is the probability that 3 adults believe plus the probability that 4 adults believe. If we've got 4, that's the maximum number of adults that could believe. So the probability that 3 adults believe, we actually calculated that already. That was this 4 times 0.4 to the third times 0.6, which turned out to be that value. We want to use the non-rounded value here to be as accurate as possible, and then we'll round at the end. And then we want to add the probability that all 4 believe. So we've got 0.0256 before rounding. And if we add these two guys together, this is what we get. 0.1536 plus 0.0256. And that equals 0.1792. Because the probability that at least 3 adults believe is the probability that 3 or more adults believe. And if we've got 4 in our group, you could have 3 that believe, or you could have 4 that believe. And then we would add those together to get that probability that at least 3 believe. So I have 0.1792. Let's go back to the homework. All right. And now we've got one last question. It says, if 4 adults are randomly selected, is 3 a significantly high number who believe in reincarnation? Remember how that works. Let me go back to my paper now. So is 3 a significantly high number that believe in reincarnation? Now remember how we determine whether a value is significantly high or significantly low when we are using probabilities. If I'm looking to test whether 3 is significantly high, I have to look at the probability that x is greater than or equal to 3, which we know that's the same as the probability that x equals 3 plus the probability that x equals 4. And we've already calculated that. That's that 0.1792. Now, if I convert this to a percentage so I can better understand it, what this tells me is that the probability that 3 people, in that randomly selected group of four people believe in reincarnation, or all 4 of them believe in reincarnation, that probability is 17.92%. That's definitely greater than that 0.05%. This is not particularly rare. Since this is not particularly rare, 3 is not a significantly high number. And again, the way we're doing that is we're just looking at the probability that x is greater than or equal to 3, and we're comparing it to 0.5. If the probability is less than or equal to 0.5, 0.05, sorry. If that probability is less than or equal to 0.05, then we'll say that that is rare and that number, that value over here is significantly high. Now, if the number is greater than 0.05, then we'll say that it's not significantly high. But again, this is the idea. We'll say that this value is significantly high if the probability that x is equal to that value or greater than that value is less than or equal to 5%. Because if it's less than or equal to 5%, then that means that value and all the values that are beyond it, that's pretty rare. And then we would say that that's significantly high. But if this value is greater than that 0.05, what we're saying is if that's a 17.92% chance that x is greater than or equal to 3, 17% is not that rare. So we're going to call that not a significantly high number of successes. So let's go back to the homework. Say no, because the probability that 3 or more of the selected adults believe in reincarnation is greater than 0.05. That's right. And that's how we answer that one.